And now in this lecture we'll answer on two questions. In the first question we find out the area of this big circle. In the second question we'll find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing we have those two circles that touch each other at this point C. This is line segment AC, is equal to 6 units in its length. This is line segment CB, that is equal to 9 units in its length. Here, this is tangent DE, that is tangent to the small circle at this point B, and it is tangent to the big circle at this point. Again, our mission is to find out the area of this big circle. Okay, so first of all, we will define the point of tendency of this tangent DE with this big circle. This point is point M. We will define the center of this big circle. This point is point O. And from the point of tendency, that is point C, we go straight line towards tangent DE. And we define the touching point of tangent, the current tangent, with tangent DE. This point is point N. In the next step, we'll focus on this current start point N. For this current start point N, we have two tangents to this small circle, tangent NB and tangent NC, and according to rule 2 they are equal to each other. That is to say, NB equals to NC. So repeat quickly rule 2. According to rule 2, the lengths of two tangents from a current standpoint to a circle are equal. In the drawing we have a circle, and this is the current standpoint point P. From this current standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement all showing of a drawing. However, if you focus on this current standpoint point N, from this current standpoint point N, we have two tangents to this small circle, tangent NB and tangent NC, and according to rule 2, they are equal to each other. That is to say, NB equals to NC. Likewise, from the same current standpoint point N, we have two tangents to the big circle, tangent NC and tangent NB, and tangent NM. According to rule 2, they are equal to each other. That is to say, NM equals to NC. According to rule 2. In the next step, we'll focus on this common external point B. Point B is an external point in relation to this big circle. So for this common external point B, we have tangent BM. Tangent BM is tangent to the big circle, and this point M. And from the same common external point B, if we draw this straight line, it will count the circle, the big circle, at 2 points, point C and point A. In this way, we can then chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. So I take quickly on rule 10. According to rule 10 is true in any circle. In any circle, if AB is any chord, AB is the chord of this circle, and PT is tangent to the circle at point T. So if from the same common start point P we have here chord AB, and from the same common start point P we have here also tangent PT. So then in this moment the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So can I try implement rule 10 in our drawing? Now drawing, if we focus on this common standpoint point V, from this common standpoint point V, we have here tangent BM, and from the same common standpoint V, if we draw a straight line, it becomes the circle at 2 points, C and A. This way we can here call CA. So the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times DA. So I'll write it down. BM square equal to BC times BA. So repeat again. If we focus on the common standpoint point B, according to rule 10, the following equation is true, that BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is. So BM square, according to rule 10, BM square equals to BC. BC is 9 times BA. BA in total equals to 16 plus 9, that is 25. So in total, according to rule 10, we have found out that BM square equals to 9 times 25. Here we'll take a root out of this equation and finally get that BM equals to the square root of 9 is 3 times the square root of 25 is 5. So in total, BM equals to 3 times 5, that is 15. So we found out that the length of this tangent BM is 15 units. BM equals to 15 units in its length. So we already found out that Cn equals to NB. Again, Cn equals to NB according to rule 2. So I'll copy triangle CNB in a new page and we'll analyze this triangle CNB. Actually, this is triangle CNB to decode from the original drawing. So in this triangle CNB, side Cn equals to side NB. And we have the rule that says that in front of equal sides in the triangle, there are equal angles. In front of this side Cn, we have this angle. In front of this side NB, we have this angle. So those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So if we found out that angle NCB, this is angle NCB, it is equal to alpha, and angle CBN also equals to alpha. This is angle CBN, that is also equal to alpha. In the next step, we join point C and M together by a straight line. By joining point C and M, we create a triangle CNM. And we already found out that CN equals to NM. So I copy triangle CNM in a new page and we analyze this triangle CNM. So actually, this is triangle CNM that according to the original drawing, we already found out that according to rule 2, side CN equals to side NM. And according to the rule that says that in front of equal sides in the triangle there are equal angles, we get that in front of this side NM we have this angle, and in front of this side CN we have this angle. So those two angles that are located in front of those two equal sides must be also equal to each other on their sizes. So if we define the size of this angle as beta, then this angle must be also equal to beta according to the rule that I mentioned. So in total, if we found out that angle MCN equals to beta, this is angle MCN that is equal to beta, and also angle CBN also equals to beta. Angle CMN, this is angle CMN that is also equal to beta. So in the next step, I'll copy the big triangle MCB in the new page and analyze this big triangle MCB. Angle MCB, this angle equals to beta plus alpha. Angle MCB equals to beta plus alpha. So okay, this is triangle MCB that I copied from the original drawing. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and it is of course true in this triangle MCB. So the sum of the angles in triangle MCB must be equal to 180 degrees. So which angles we have in triangle MCB? This is angle alpha, plus this is angle beta, plus the third angle that is beta plus alpha, In total, the sum of those three angles must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In this side of the equation, we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, is equal to 180 degrees. Here we divide this equation by 2 and find that 2 alpha over 2 is alpha, plus 2 beta over 2 is beta. So alpha plus beta equals to 180 degrees over 2 is 90 degrees. So we found out that alpha plus beta equals to 90 degrees. That is to say, this angle is a right angle. Simply, this is angle alpha plus beta, that is a right angle, according to what we just now found out. So this is a right angle. The big angle MCB is a right angle. Again, this is angle MCB, that is a right angle. It is given as the equation that AB is a straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees, according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So if I found out that angle ACM, this is angle ACM, is a right angle. In the next step, we join points A and M together by straight line. And we'll focus on the big circle. On the big circle, we have peripheral angle ACM. This is peripheral angle ACM, and the size of this peripheral angle ACM is 90 degrees. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And therefore, this peripheral angle ACM, that is a right angle, it must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore, according to rule 5, AM must be the diameter of the circle. So, already know, according to rule 5, we found out that AM is the diameter of the circle. According to rule 5, AM must be the diameter of the circle. The diameter of the big circle, of course. AM is the diameter of the big circle. But we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And therefore, the center of this big circle must be located on 9 segment AM, that is the diameter of the circle. So, here, at this point on 9 segment AM, it is actually the center of this circle. So point O is the center of this circle, and point O is definitely located on AM, that is the diameter of the circle. So point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle. We define the radius of this big circle as R, so OM equals to R. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, in the next step, I'll copy the right big triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. AM is the missing side, MB equals to 15 units according to rule 10, and the hypotenuse AB, in total it is equal to 16 plus 9, that is 25. So actually, this is the right triangle A and B that are correct from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. So I'll write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. AB is 25, therefore AB squared is 25 square, that is 625, and it is equal to AM squared. AM is the missing side, so whether it is plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we can find out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 425 is 400. So 400 equals to AM squared. Here we take out of this equation, and we get that AM equals to the square root of 400, that is 20 units. So AM equals to 20 units in its length. We have already found out that AM, according to rule 5, AM is the diameter of the circle, the diameter of the big circle. So this is line segment AM, that is the diameter of the circle. And we just right now found out that the diameter of the big circle is equal to 20 units. If the diameter AM is 20, it means that the radius must be equal to half of it. So the radius R of this big circle must be equal to the diameter AM over 2. The diameter AM is 20 and 20 over 2 is 10. So in total we found out that the radius R of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle, the area of the big circle, must be equal to pi times the radius of the big circle, that is 10 squared. So the area of the big circle in total must be equal to pi times 10 squared. So it is pi times 10 squared. 10 squared is 100. So in total we found out that the area that we are looking for this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of the big circle equals to 314.159 square units. Repeat again, we actually found out that the area that we're looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So, in the drawing, we have rectangle ABCD, and we have also this semicircle. We know that this is 9 segment AEM, that is equal to 5 units in its length. And we also know that side DC of rectangle ABCD is tangent to the semicircle at this point. Again, our mission is to find out the area of this rectangle ABCD. So we'll start with the first method. First of all, we know that all those four angles inside rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle. And finally, this is a right angle. In the next step, we'll define the center of this semicircle. This point is point O. We'll define the point of tendency of tangent DC with this semicircle. This point is point E. In the next step, we'll join points O and E together by a straight line. Point O is the center of the semicircle. Point E is a point on the semicircle itself. Therefore, OE is the radius of this semicircle. We'll define the radius of this semicircle as x. Therefore, OE, that is the radius of the semicircle, is equal to x units in its length according to our definition. OE equals to x. The radius OE of this semicircle is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius OE. If DC is perpendicular to OE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, you can here quadrilateral ADEO. Inside this quadrilateral ADEO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at its right angle if not a square. So we relate to quadrilateral DEOA as a right angle because it has 4 right angles. So I write it down. This is right angle. Quadrilateral DEOA is a right angle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side OE must be equal to the opposite side DA. But OE is x, it is the radius of the circle, that is equal to x, therefore DA must be also equal to x units in its length. Point O is the center of the circle. Point A is the point of the circle itself. Therefore, OA is also the radius of this semicircle, that is equal to x. In the next step, we'll define the length of this line segment OB as A. And we'll define the length of this line segment MB as B. In the next step, we join points O and M together by straight line. Point O is the center of the semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle, that is equal to x. In the next step, I will copy the right triangle OMB in a new page, and we'll implement the Pythagoras theorem on this right triangle OMB. Here by PT is the abbreviation for Pythagoras theorem. So this is the right triangle OMB that I got from the drawing. According to the Pythagoras theorem, in this right triangle OMB, OM squared, that is the square of the hypotenuse, is equal to MB squared plus BO squared. So I'll write it down. So OM squared, that is the square of the hypotenuse, is equal to OB squared plus MB squared. OM is x, therefore OM squared is x squared. And it is equal to OB squared. OB is a, therefore OB squared is a squared plus MB squared. MB is b, therefore MB squared is b squared. So in total, according to equation 1, we actually found out that x squared equals to a squared plus b squared. In the next step, I'll copy the right triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right big triangle, triangle A and B. Side AB in total equals to x plus a. AM equals to 5 units in its length, according to what is given us in the question. Here by PT is the equation for Pythagoras theorem. Actually, this is the right triangle A and B that I call it from the original drawing. In this right triangle A and B, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, equals to MB squared plus BA squared. So I'll write it down. AM squared, that is the square of the hypotenuse, is equal to MB squared plus AB squared. AM is 5, therefore AM squared is 5 squared, that is 25. And it is equal to MB squared. MB is b, therefore MB squared is b squared plus AB squared. AB is x plus a, therefore AB squared is x plus a squared. So in total, according to equation 2, we found out that 25 equals to b squared plus a, again 25 equals to b squared plus x plus a squared. So according to equation 2, 25 equals to b squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a. In this side of equation 2, we have b squared plus a squared. But according to equation 1, we already found out that b squared plus a squared equals to x squared. Therefore, we substitute b squared plus a squared in this equation 2 by x squared from equation 1. We do it now and we get that according to equation 2, 25 equals to b squared plus a squared is x squared according to equation 1 plus x squared plus 2 times x times a. So according to equation 2, we should find out that 25 equals to x squared plus x squared is 2x squared plus 2xa. Here we divide this equation 2 by 2. And we will get that 25 over 2 is 12.5 and 2x squared over 2 is x squared plus 2xa over 2 is xa. So in total I can find out that 12.5 equals to, here we take out x as a common factor from those two expressions. So we took x as a common factor, inside the brackets we have x plus a. So in total, according to equation 2, we should find out that x times x plus a equals to 12.5. X times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Actually, the area of a rectangle, or again, our mission is to find out the area of rectangle ABCD. The area of any rectangle equals to the length of the rectangle times the width. And therefore the area of rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length is AB times the width. The width is AD. So in total we can find out that the area of rectangle ABCD equals to AB times AD. AB is the length, AD is the width. AB in total equals to x plus a. AB equals to x plus a. Times AD. AD equals to x. So in total we should find out that the area of rectangle ABCD equals to x plus a times x. But we already found out that x plus a times x equals to 12.5. X plus a times x equals to 12.5. Therefore we can substitute x plus a times x in this equation by 12.5. X plus a times x equals to 12.5. So in total we found out that the area that we are looking for in this question, that is the area of rectangle ABCD, is equal to 12.5 square units. I repeat again, the area of this rectangle ABCD is equal to 12.5 square units. We finish with the first method. In the next step I present to you how to find out the area of this rectangle ABCD according to the second method. So because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x. Okay. So point O is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. That is equal to x units according to our definition. We have already found out that in the first method that AD also equals to x. AD is also the radius of the semicircle is equal to x. So I will not repeat on the same process that we have already done in the first method. We have already found out that AD equals to x units in its length. Okay. In the next step, we define the length of this line segment OB as A. We define this point as point N. In the next step, we join points M and N together by a straight line. By doing this construction, we can do peripheral angle NMA. This is peripheral angle NMA, and peripheral angle NMA subtend on AN. Again, peripheral angle NMA subtend on AN. AN is of course the diameter of the semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle is equal to 90 degrees in its size. So I'll click quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle. Line segment AB is the diameter of this circle. And we have here also, this is peripheral angle ACB, and because of the fact that peripheral angle ACB subtends on AB, that is the diameter of this circle, the size of this peripheral angle ACB must be equal to 90 degrees. Again, because of the fact that peripheral angle ACB subtends on AB, that is the diameter of this circle, the size of this peripheral angle ACB must be equal to 90 degrees. So we can implement rule 7 in our drawing. Why? Because in our drawing we have, this is peripheral angle NMA that subtends on AN, that is the diameter of this semicircle, and therefore according to rule 7, the size of this peripheral angle NMA must be equal to 90 degrees. And this angle NMA is a right angle according to rule 7. In the next step, we define this angle as angle alpha. So, and we focus on this right angle, triangle AMN. In the right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the next step, we'll focus on this right triangle, triangle A and B. In this right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. This is the sum of the angles in any triangle. In the next step, I will copy this right triangle A and B, and this right triangle A and N in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. AN is the diameter of the semicircle. The radius of this semicircle is x, therefore the diameter must be twice as big as the radius. Therefore, the diameter must be equal to 2x. So AN equals to 2x units in its name. Actually, those are the two right triangles A and N and A and B that are going to the drawing. So in the next step, we'll prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle ABM. In the right triangle A and B, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN, they are both equal to 90 degrees, and therefore they are equal to each other. In addition, this angle is a common angle that belongs to both triangles. Okay, so we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to angle A as it is belongs to the right triangle AMN, it will be defined as angle MAN. And angle A equals to itself, so if we relate to angle A as it is belongs to the right triangle AMB, it will be defined as angle MAB. So angle A equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So finally, this is angle AMN in the right triangle A. This is angle AMB in the right triangle AMB, and it is equal to this angle. This is actually angle MNA in the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the triangles of this right triangle AMB are correspondingly equal to all those triangles of the right triangle AMN. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So if we prove that this right triangle AMB is similar, this is the sum of similar to the right triangle AMN according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AM on this right triangle AMB over side AN of this right triangle AMN is equal to side AB in this right triangle AMB over side AM in this right triangle AMN. So I repeat again. We derive that side AM in the right triangle AMB over side AN in the right triangle AMN equals to side AB in the right triangle AMB over side AM in the right triangle AMN. AM is 5 over AN. We only found out that AN is the diameter of the semicircle, that is 2x. And it is equal to AB. AB is x plus A over AM. AM is 5. So in total, according to equation 1, we should find out that 5 over 2x equals to x plus A over 5. Here we first multiply this equation and equation 1. And we get that 5 times 5 is 25 equals to 2x times x plus A. Here we divide this equation 1 by 2. Finally get that 25 over 2 is 12.5, and it is equal to 2x over 2 is x, so it is, in total this expression equals to x plus a. So I shall find out that according to equation 1, x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. The area of any rectangle equals to the length of the rectangle times the width. The area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length of this rectangle ABCD is AB. Times the width. The width is AD. So in total, we found out that the area of rectangle ABCD equals to AB times AD. AB is x plus a, and AD is x. So in total, the area of rectangle ABCD equals to x times x plus a. But according to equation 1, x times x plus a equals to 12.5. Therefore, we substitute x times x plus a by 12.5. So actually, in both methods, we found out that that we're looking for in this question, that is the area of this rectangle ABCD is equal to 12.5 square units. We finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this big circle. So, in the drawing, we have two circles that touch each other at this point, or they are tangent to each other at point C. In addition, we know that this is line segment AC, that is equal to 16 units in its length. This is line segment CB, that is equal to 9 units in its length. And we also have here tangent DE, that is tangent to this small circle at point B. And tangent DE is also tangent to the big circle at point M. Again, our mission is to find out the area of this big circle. So first of all, if we focus on this common standpoint B, point B is a common standpoint in relation to this big circle. So if we focus on this common standpoint point B, from this common standpoint point B, we have here tangent VM, and from the same common standpoint point B, if we draw a straight line, it will cut the big circle at 2 points, point C and point A. In this way, we get here called AC. So all the requirements of rule 10 are satisfied, and therefore we can implement a rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I repeat again, if we focus on the common standpoint point B, according to rule 10, the following equation is true: that BM square equals to BC times BA. BM is the missing side, so we leave it as it is. and it is equals to BC. BC is 9 times BA. BA in total equals to 16 plus 9, that is 25. And again, BC is 9, BA is 25. So in total, according to our test, we actually found out that BM squared equals to 9 times 25. Here we took a root out of this equation and finally found out that BM equals to the square root of 9, that is 3, times square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So we actually found out that the length of this tangent MB is 15 units. In the next step, we need a construction, that is to say, from this point C, that is the point of tendency of the two circles with each other, we draw a straight line towards tangent DE. And we define the touching point of the common tangent with tangent DE. This point is point N. Cn is actually a common tangent that belongs to both circles. Cn is tangent to the small circle, and Cn is also tangent to the big circle. Both points of tendency are located at point C. So we have here, we focus in the next step at point N, from the common standpoint point N. We have two tangents to the small circle, tangent NB and tangent NC. And according to all two, they are equal to each other. That is to say, NB equals to NC. So in the next step, I copy triangle CNB in a new page. Analyze this triangle CNB. This is triangle CNB that are going from the original domain. According to rule 2, Cn equals to NB. And we have the rule that states that in front of equal sides in the triangle there are equal angles. In front of this side Cn we have this angle CBN, and in front of this side NB we have this angle, NCB. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other. So if we define the size of this angle as alpha, then this angle must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. So in total, we found out that angle NCB equals to alpha and angle NBC also equals to alpha. This is angle NCB, this is equal to alpha, and this is angle CBN, this is also equal to alpha. We'll continue to focus on this common standpoint point N. From this common standpoint point N, we have two tangents to the big circle, tangent NM and the tangent NM and tangent NC. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, we join point C and M together by straight line. When joining point C and M, we get that here, triangle MCN. In the next step, I copy triangle MCN in a new page, and we analyze this triangle MCN. This is actually triangle MCN that I copy from the original drawing. We already found out that Cn equals to Nm according to rule 2. And according to the rule that said that in front of equal sides in the triangle there are equal angles, so in front of this side Cn we have this angle, and in front of this side Nm we have this angle. And those two angles are located in front of those two equal sides, and therefore they must be equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to better, because they must be equal to each other. So in total, we found out that angle NCM equals to beta, and this is angle CMN that is also equal to beta. Again, this is angle MCN that is equal to beta, and this is angle CMN that is also equal to beta. In the next step, I copied the right big triangle MCB in the new page, and analyze this right big triangle MCB. So actually, this is triangle MCB that are going from the original drawing. We already found out that this angle equals to alpha, this angle equals to beta, and the big angle MCB equals to alpha plus beta. Yeah. The big angle MCB equals to alpha plus beta. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle MCB must be equal to 180 degrees. So which angles we have in triangle MCB? We have angle alpha plus angle beta plus angle beta plus alpha. Alpha plus beta plus alpha, in total they must be equal to 180 degrees. So on this side of the equation we have alpha plus alpha, that is 2 alpha, plus beta, that is 2 beta. So in total, in this side of the equation we have 2 alpha plus 2 beta, that is equals to 180 degrees. We divided this equation by 2 and found out that alpha plus beta equals to 180 degrees, that is over 2, that is 90 degrees. So we found out that this is the big angle alpha plus beta, that is actually angle MCB. Angle MCB is the right angle. It is equal to 90 degrees in its size. We know that AB, according to what is given in the question, AB is the straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees, according to all three, that states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AB at point C? We have this angle, that is a right angle, plus this missing angle. In total it must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. So we found out that angle ACM is a right angle. In the next step we join points A and M together by a straight line. And we focus on the big circle. Inside this big circle we have peripheral angle ACM. Peripheral angle ACM is equal to 90 degrees in its size. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And because of the fact that this is peripheral angle ACM that is equal to 90 degrees, according to rule 5, this peripheral angle ACM must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore AM must be the diameter of the circle according to rule 5. And again, according to rule 5, AM is the diameter of the big circle because of the fact that the size of peripheral angle ACM is 90 degrees, and according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore AM must be the diameter of this big circle. Again, AM is the diameter of the big circle. And we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. So AM is the diameter of this big circle, and therefore the center of this circle must be located somewhere on AM. So this is point O, that is a point on the diameter AM, and point O is the center of this circle. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle. OM is the radius of the big circle. We define the radius of the big circle OM is R. Because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied this right big triangle A and B in a new page, and we implemented the Pythagoras theorem on this right big triangle A and B. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle A and B that is copied from the original drawing. A and B equals to 15 units according to rule 10. AB in total equals to AC, that is 16. plus CB, that is 9. 16 plus 9 is 25. So according to the Pythagoras theorem, this right triangle AMC, AB square equals to AM square plus MB square. Again, AB square equals to AM square plus MB square. AB is 25, therefore AB square is 25 squared, that is 625. And it is equal to AM square. AM is the missing sign, so we leave it as it is. So it is AM square plus MB square. MB is 15, therefore MB square is 15 squared, that is 225. So in total we found out that 625 equals to AM square plus 225. Here we subtracted 225 from this equation, and we found out that 625 minus 225 is 400, so 400 equals to AM square. Here we took out the root of this question, and found out that AM equals to the square root of 400, that is 20. So AM equals to 20 units in its length. AM is the diameter of the big circle. So the diameter of the big circle equals to 20 units in its length, and therefore the radius of the big circle R must be equal to half of it. That is to say, the radius R must be equal to the diameter AM over 2. The diameter AM is 20, so the radius must be equal to 20 over 2. 20 over 2 is 10. So in total we should find out that the radius of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. The area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle, that is 10 squared. So it is pi times 10 squared. 10 squared is 100. So in total the value of this expression is 100 pi. So if you found out that the area of this big circle must be equal either to 100 pi square units, so in terms of numbers, the area of this big circle is equal to 314.159 square units. We finish with the first question. In the next step, I present to you the second question, and we solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD, and we have also this semicircle. This is 97 AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. We start with the first method. First of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the point of tendency of delta DC with this semicircle as E. In the next step, we join point O and E together by side line. Point O is the center of this semicircle. Point E is the point on the semicircle itself. Therefore, OE is the radius of this semicircle. We define the radius of this semicircle as x, so OE equals to x. Because of the fact that the radius OE is equal to x, the radius OE of this semicircle is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever your radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius OE. If this is perpendicular to OE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do the quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral DEOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But OE is x, therefore DA must be also equal to x units in its length. Okay, so in the next step, we define this line segment OB as A and this line segment MB as B. In the next step, we join points O and M together by side line. Point O is the center of the semicircle, point M is the point of the semicircle itself. Therefore, OM is the radius of this semicircle that is equal to X units according to our definition. In the next step, I copied the right triangle OMB in a new page and we implemented the Pythagoras theorem on this right triangle OMB. So okay, this is the right triangle OMB that I copied from the original drawing according to the Pythagoras theorem. This right triangle OMB, OM square equals to MB square plus BO square. OM is X, therefore OM square is X square, and it is equals to OB square, OB is A, therefore OB square is A square, plus MB square. MB is B, therefore MB square is B square. So in total, according to equation 1, we actually found out that X square equals to A square plus B square. In the next step, I copied this right triangle A and B in the new page and we implemented the Pythagoras theorem on this right triangle, triangle A and B. This is the right triangle A and B that I copied from the original drawing. Side AB equals to X plus A, side MB equals to B, according to our definition. MA equals to 5 units, the hypotenuse MA equals to 5 units, according to what is given in the question. This right triangle A and B, AM square equals to MB square plus BA square. AM is 5, therefore AM square is 5 square, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square, plus AB square. AB is X plus A, therefore AB square is X plus A square. So 25 equals to B square plus X plus A square. X plus A square equals to X square plus A square plus 2 times X times A. In this equation 2, we have the expression B square plus A square, but according to equation 1, B square plus A square equals to X squared. Therefore, we can substitute B square plus A square in this equation 2 by X square from equation 1. We did it and we found out that 25 equals to B square plus A square is X square plus X square plus 2XA. So 25 equals to X square plus X square is 2X square plus 2XA. So in total 25 equals to 2X square plus 2XA. Here we divided this equation 2 by 2 and finally found out that 25 over 2 is 12.5 and it is equal to 2x square over 2 is x square plus 2xa over 2 is xa. So in total, according to equation 2, we found out that 12.5 equals to x square plus ax. Here we took out x as a common factor from those two expressions, so inside the brackets we left with x plus a. So in total, according to equation 2, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Our mission is to find out the area of rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is AB, and the width is AD. And then the length is AB, and the width is AD. AB equals to x plus a, and AD equals to x. Again, AB equals to x plus a, and AD equals to x. So in total, the area of rectangle ABCD is x plus a times x. But x plus a times x equals to 12.5. Therefore, we can substitute x plus a times x by 12.5 from equation 2. So in total, we shall find out that the area of this rectangle ABCD is equal to 12.5 square units. We finish with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. First of all, we know that all the 4 angles inside this rectangle ABCD are right angles. So those 4 angles are all right angles. We define the center of this semicircle, this point as point O. And we have already found out in the first method, we define the radius of this semicircle as x. And we have already found out that in the first method, the dA equals to x. In the next step, here point O is the center of the semicircle, point A is the point of the semicircle itself, therefore always the radius of this semicircle is equal to x. According to our definition, we define this line segment OB as A. We define this point as N, and join points N and M together by side line. By doing this construction, we get the peripheral angle NMA. This peripheral angle NMA subtends on AN, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And therefore this peripheral angle NMA must be equal to 90 degrees because it subtends on NA, that is the diameter of the semicircle. So this angle NMA equals to 90 degrees according to rule 7. Okay, so in the next step, we define this angle as alpha. And focus on this right triangle AMN. In the right triangle AMN, this angle equals to alpha. This angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the right triangle AMB. The right triangle AMB, this angle equals to alpha. This angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees minus alpha. In the next step, I call it the right triangle AMB, the right triangle AMN in the new page, and prove that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles AMN and AMB that are coming from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And finally, this is angle A, that is a common angle that belongs to both triangles, so we can write out that angle A equals to itself is a common angle that belongs to both triangles. So in total, we shall prove that all the triangles of the right triangle A and B are correspondingly equal to all the triangles of the right triangle AMN. And therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that AM over AN equals to AB over AM. We derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5, AN is 2x, AB is x plus A, and AM is 5. So in total, we can find out that 5 over 2x equals to x plus A over 5. Because multiply this equation and find out that 5 times 5 is 25, so 25 equals to 2x times x plus A. We divided this equation by 2 and found out that 25 over 2 is 12.5, 2x over 2 is x. So in total, we actually found out that 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle ABCD. Actually, the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of the rectangle ABCD must be equal to the length that is AB times the width that is AD. So in total, the area of the rectangle ABCD must be equal to AB times AD. AB is x plus A, and AD is x. AD is x. So in total, the area of the rectangle ABCD must be equal to AB, that is x plus A, times AD, that is x. So in total, the area of the rectangle ABCD must be equal to x plus A times A. But x plus A times A is 12.5. So we substitute x plus A times x by 12.5. So in total, we shall find out in both methods that the area of this rectangle ABCD is equal to 12.5 square units. Okay, thank you very much.